For decades, we thought we had a pretty good handle on the sun's heartbeat, that famous 11-year cycle of activity. But what if the main engine we believed was driving the whole show just isn't there? Today, we're going to dive into a new theory that might just rewrite everything we thought we knew about our star.
It's really one of the biggest questions in all of solar physics. I mean, think about it. Every 11 years, like clockwork, the sun goes from being relatively calm to this raging tempest of sunspots and solar flares, and then right back to quiet again. This rhythm is incredibly reliable, but the actual mechanism behind it, well, that's been a massive puzzle for a long, long time.
Okay, so here's how we're going to break this down. First, we'll look at the sun's predictable patterns, the clues it gives us. Then we'll get into the classic conveyor belt theory and the huge problem it ran into. After that, we'll introduce the new kid on the block, a new model, and see how it solves a key puzzle. And finally, we'll explore what it all means if the sun's engine is way closer to the surface than we ever imagined.
Right, so before we dive into all the competing theories, we have to start with the evidence. The sun isn't just some chaotic ball of fire, not at all. It has this very specific rhythmic heartbeat that gives us these beautiful, consistent clues about what's happening deep inside.
And maybe the biggest clue we have is this thing called the sunspot butterfly diagram. It's awesome. At the very start of a cycle, sunspots pop up at the sun's mid-latitudes. But then, as those 11 years tick by, new spots start showing up closer and closer to the equator. And when you plot all that activity over time, the pattern it creates looks just like a butterfly's wings. So here's the deal. Any theory that tries to explain the solar cycle has to be able to explain this pattern. It's non-negotiable.
For a long, long time, the reigning champion of theories was something called the flux transport dynamo model, or FTD. The easiest way to picture it is to think of a giant, elegant conveyor belt system running deep, deep inside the sun.
So the FTD model worked in this really cool three-step dance. It starts at the surface, where old, decaying sunspots create this simple north-south magnetic field, kind of like a giant bar magnet. This is called the poleward field. Then came the crucial part. A massive conveyor belt of plasma was thought to grab that surface field and drag it way down deep inside the sun. And finally, deep down, the sun's crazy rotation would stretch and twist those fields into powerful east-west bands, the toroidal field, which would then bubble up to the surface to create the next generation of sunspots.
So the central idea of this model was super simple. That deep conveyor belt was the sun's master clock. If the belt moved faster, you got a shorter cycle. If it moved slower, you got a longer one. It was this beautiful, elegant explanation that seemed to fit everything perfectly. But there was one teensy little problem.
The theory was beautiful, no doubt, but the observations just weren't lining up. The entire model depended on finding that deep conveyor belt, and, well, it was proving to be incredibly hard to find.
And this is the question that started to pull on the one thread that could unravel the whole thing. For decades, scientists have been using this amazing technique called helioseismology. It's basically like studying sound waves moving through the sun to map its interior. And they were looking for this simple, single conveyor belt. What they found, or rather, what they didn't find, created a huge problem for the theory.
Instead of a simple, clean conveyor belt, the data showed a messy, complicated reality. Some studies even suggested the deep flow was moving in the exact opposite direction the theory needed it to. Others found a bunch of churning, smaller cells of plasma instead of one smooth current. The bottom line was this: the engine for the entire model just couldn't be found. The theory's most important assumption was suddenly on very, very shaky ground.
But this is where science gets really exciting, right? Because when a key piece of a theory goes missing, it opens the door for a brand new idea to walk right in.
So meet the challenger, the distributed-shear dynamo model. Okay, the name's a bit of a mouthful, but the idea behind it is a radical simplification. It basically says you don't need a special engine room deep inside the sun. Instead, the magnetic field generator, the dynamo, is spread out, or distributed, throughout the entire convection zone, that big, churning upper layer of the sun. The action is happening much, much closer to the surface than we ever thought.
So, this slide really sets up the showdown. The old FTD model, it put the engine way down deep and said that deep flow was the star of the whole show. This new distributed shear model says, nope, the engine is spread all over the place up here, and that deep flow, it has a minimal role at best. It's a complete 180 in perspective.
But look, a new theory is only as good as its ability to explain the evidence we can actually see. So the big question is, how does this new model create that iconic butterfly diagram without its main character, the deep conveyor belt?
And this is the absolutely stunning part. Researchers ran the simulations, and they found their new model could reproduce that butterfly pattern perfectly. And get this, it worked even when they told the simulation that the deep flow was messy, or broken, or even flowing in the wrong direction. All the conditions that make the old model just completely fall apart. So how on earth does it do it?
Okay, this is so clever. The new model says the butterfly pattern isn't caused by something being physically moved from one place to another. It's actually an illusion created by timing. You see, the sun spins faster at its equator than at its poles, and this difference in speed generates magnetic fields most efficiently at the mid-latitudes. That's why sunspots show up there first. It just takes more time for the fields to build up to sunspot strength closer to the equator. The pattern we see moving towards the equator isn't something being carried there. It's a wave of generation. That's a huge shift in thinking.
And this just completely rewrites the rulebook. Remember that simple formula from the old model? Faster conveyor belt equals a shorter cycle? Well, the new model just snaps that link in half. In fact, some of its simulations showed that a faster deep flow can sometimes lead to a longer cycle. The whole idea of a master clock deep inside the sun just gets tossed out the window. The timing is actually controlled by stuff happening much closer to the surface.
So what's the big takeaway from all of this? It really represents a fundamental shift in where we even look for the sun's engine.
Now, it's really important to clarify something. This new model isn't saying that all plasma flows don't matter. Not at all. It demotes the deep, unobservable flow to a minor character. But it actually elevates the role of the flow we can see, the flow moving towards the poles right on the sun's surface. That surface flow is absolutely essential for recycling the magnetic fields from old sunspots to lay the groundwork for the next cycle.
So here's the ultimate takeaway. For years, we were searching deep inside the sun's guts for its magnetic engine. This new model suggests we might have been looking in completely the wrong place. The real control panel might be much shallower, governed by the physics of the sun's churning surface, the part we can actually watch every single day. This isn't just a small tweak. It fundamentally changes our entire understanding of the solar cycle.
And this just leaves us with a fascinating final thought. For decades, the search for answers took us deeper and deeper into the sun's mysterious interior. But if this new model holds up, it means some of the sun's biggest secrets might not be buried in its core at all. They've been hiding right there in plain sight, on the surface, just waiting for us to finally see them.